Welcome once again to the physics video lecture. This is Physics 105A video lecture 26. We're going to begin with a quick review on what the exam problems were. And I think I'll just mainly write up the answers. So we had, for the first problem, the position A cos omega t, B sine omega t, and 0 Cartesian coordinates. And what did we want there? First of all, we wanted to show that this trajectory traces out an ellipse. So since this is our x, and this is our y, and this is our z, we can actually just read it off. X squared divided by a squared is cosine squared. Y squared divided by b squared is sine squared. Cosine squared plus sine squared equals 1. Okay, so it does trace out an ellipse. X squared over a squared, y squared over b squared equals 1. Another interesting thing about this object here is if you just calculate the velocity and the acceleration, if you multiply the acceleration by m, you get minus m omega squared and the original r. Okay, a, b, and omega are constants, t is the time. So we're actually going to use this thing in a couple of days because that's going to be our first example of a central force, namely a force that's directed back towards the origin. That's our minus sign, directed back towards the origin, proportional to r. So we're actually going to work with this, but that was a part of the problem. And if you calculated L, which was R cross M R dot, you found M omega AB, right? M omega AB K hat. So that's interesting also. We haven't really talked about angular momentum yet. That's more something for next semester. Well, actually for later this semester. But what we do find is the angular momentum is, so if this is the xy plane and we're doing this ellipse, and the angular momentum is perpendicular to the xy plane, k hat direction, and its magnitude is constant. So that too is going to be something we discover about central forces. Okay, so that's a great problem. The next one, we've got m dv dt, we're in one dimension now, is equal to minus a positive constant d to the 3/2 power. Okay, so that's a friction of some type. We just made it up, right? So what do we get? If we integrate it, we find v of t equals, there's a couple ways to write this down. 1 divided by 1 over root v0, yes, a little awkward, plus ct over 2m squared. Okay, so there's the answer. So when t is equal to 0, 1 over root v0 squared. So yes, you get v sub 0 when t is equal to 0. And you could express it slightly differently. You could multiply top and bottom by v sub 0, for example, to make things a little more clear. Not necessarily simpler. However, the next point is that as t goes to infinity, or t has to reach infinity, t has to diverge for v to come to a stop. So this thing comes to a stop you know, as t goes to infinity. On the other hand, there's a finite distance traversed. The way to find the finite distance, you could work with this, but it might take you longer. The way to find the finite distance is to write our differential equation as m dv over dx times v is equal to minus cv to the 3/2. And then separate variables and integrate this. And then you will get v of x, and you can finally find that the total distance traveled will be 2m v0 to the 1/2 divided by c. Okay, so that'll be the total distance traversed. So I'm not going to say much more about these because you might want to go back in and figure it all out yourself, okay, and work through the problem again. Finally, we have problem 3. So this is just something that has good shape. So we have potential energy A over the root of x plus b times the square root of x. And if you want to graph this, and we restricted x to the positive axis, and a and b were positive. So a good way to look at these is to know these basic functions. So a over the root of x is just generically going to diverge here, come down like that, much like some other functions we've dealt with. Square root of x goes up like that. So when you add those, and you're going to have something like this, and you clearly have a local minimum at x of 0. Good, so we were going to find a couple of things. I'm just going to write, because you know, your first derivative criteria, you're going to get x of 0 is equal to a over b. Now for a particle of mass m moving in this potential, you have to get the second derivative, so omega squared is equal to, all right, omega. Root u double prime evaluated at x0 divided by m. And in this case, after a little bit of algebra, what do we get? We get root b to the 5/2 power 2m a to the 3/2. Okay. So you know, I'll put as a homework, I usually do this in the face-to-face world, that anything you didn't get, you go ahead and put it on your next homework, just to make sure you understand these problems. Because when you have more time than an hour to work with them, you can figure every last little bit out. And they're good problems. I think you'll enjoy them. Good. So I'll just write homework. Rework exam problems. Just for fun. Okay. Next, what we have is to wrap up our discussion of Fourier series. And we can go on and on with that, but we do have to move on. But we want to get to the Fourier integration because it's going to tie back into what we did with our harmonic oscillator, driven oscillator. So we have to make contact with that. Good. So next, more Fourier series. Let's go ahead and call it Fourier series and integrals. And I think I mentioned before, when we're all done with this, you could boil it all down to 1 page or 2 pages, you'd have a useful compendium. Good. So here's what we have. We're using the complex form, and you'll see why. K is all the integers, e to the I kx. We've had some nice examples of this, and it's a series expansion in trigonometric functions. If f of x is a real function, then these combinations will also turn out to be real. Even though individually c sub k is complex, e to the I kx is also complex. The c sub k, the coefficients, 1 over 2 pi integral minus pi to pi f of x e to the minus I kx dx. And I'll draw your attention to the point that we're integrating over the x, so this label k is found right there, right? That k is that same k right there. The x we're integrating over, we can use any variable we want there, okay? Okay, next, we had extended the interval. Remember, this was minus pi to pi. We had extended it from minus L to L. And we saw that was just a trivial substitution. So that's, I'm going to write that down. And then we're going to try to take the minus L to L out to infinity, at which point we'll actually have something new and very interesting. Okay, so minus pi to pi or minus L to L, it's really all the same thing. So for functions on the interval minus L to L, what do we have? We have f of x, we're still summing, we're summing over k, c sub k e to the I k, but now since the interval's been stretched, we have to stretch this in this way, pi over L times x. Then when x is equal to L, we're at the I k pi. And here our c sub k is equal to 1 over 2L minus L to plus L f of x e to the minus I k, got our pi over L x dx. And it's still labeled by the k there. Okay, so next, and I'll try to even fit it on this board right here, we want to extend minus L, we want to extend L to infinity. So it'll be a function over the entire real axis. And when we do that, we're going to turn this sum into an integral. And the result will be very symmetric. Okay? This sum is just begging to be turned into an integral. Okay? But it's not quite trivial because we can't just send L out to infinity because something's going to happen here as well, right? We can't just send L out to infinity in these exponentials. So there's a tricky and interesting limit that's taken, and I'll kind of talk about it a bit as well. Primarily, I want to get to those formulas. Okay, so let's go ahead and write next the interval minus infinity to infinity. Okay, so we want functions on the entire real axis. So here's what we're going to do. We're going to plug this into here and try to do that. So we're starting with minus L to L. We want to take that limit So first, we're going to plug this in. So we've got f of x equals, got a sum over k. Now the c sub k, I'm going to plug in. So, and I'll put a little bracket around it. 1 over 2L integral minus L to positive L f of u. Okay, I'm going to change the name of the variable. We're just integrating over x. Okay, it's all about the k right there. So f of u e to the minus I k pi over L u du. Okay, and then e to the minus I k pi over Lx. Yes, okay, so that's this one gets a plus sign. Okay, so far so good. I just plugged that definition in there. Now I want to interpret this, so instead of an equal sign, I'm just going to put a squiggle here. I want to interpret this as an integral, and my dk for this integral is, at the moment, it's just the unit of 1. So let's do this. We're going to have an integral, okay, and since I'm summing over k, my dk is just a unit wide. But I'm going to have I'll write delta k, right? Delta k right here is just equal to 1. Okay. So that's what this represents. Now here I can have a 1 over, now I'm going to do it different. Okay, 1 over 2L, what I have, and that L is going to infinity. What I'm going to do is pull out a pi over L. That's actually going to be my new infinitesimal when I take L to infinity. So pi over L, then I have, and that's just a constant, then I have 1 over 2 pi. Okay, pi cancels 1 over, okay, 1 over 2 pi integral f of u e to the minus I k pi over L u minus x. Okay, I brought this one in. Got the minus L to L. And I've got the du. Du comes in here as well. Du. Okay. So this is really that sum here, but you can see when the L gets large enough, this pi over L gets small. That's going to be our infinitesimal, our new infinitesimal for the integration. So let's keep going. So what we're going to do next, now let kappa be equal to k pi over L, d kappa be equal to pi over L dk. Okay. Now the dk is still a unit, right? That, like I've been saying, that delta k is still a unit, an integer, but this d kappa is going to get smaller and smaller as L goes to infinity because it's pi over L. So let's see what we get here now. So now we get, we've got the d kappa we have 1 over 2 pi integral f of u e to the minus I kappa u du, and then I'll have e to the I still kappa x. Okay, now later on I may come back and do the fully rigorous double Riemann sum that's here. But what we're going to do is take this, so let L go to infinity, and when L goes to infinity we end up with both of these minus infinity to plus infinity. Okay, this is still f of x. Okay. And at that point, we've taken those limits, and you know, I'm going to put a note here. The Riemann sum has 2 limits. And here's, I'll talk about the problem right now. You want to, you know, you're having a limit minus infinity to plus infinity on the first one here, which was your sum. And you have it for this pi over L. You can't just take that limit without getting pi over L to vanish. And the way you do it, you've got 2 limits where, I'll show this to you guys later on sometime here, where your sum of L is proportional to n for the one sum, and the other sum here, say the outside one, goes to n squared. Outside integral limits, say n squared, and so then you can actually take both limits at the same time. Very interesting. But we're going to stay where we are right here and assume that we made it work, because essentially we did. It's an interesting thing to set up, like I said, because here we can actually take this at face value, and it doesn't matter if we call it kappa or k or whatever. I'll use another color. This now, if you compare it to what we have up here, okay, this now is our Fourier coefficient, and the Fourier series is the function integrated over e to the I kappa x. So I'm going to change the name of kappa back to k because it's standard. Okay. So this is our c sub k, or c sub kappa, if you want, where kappa is a continuous variable and not an integer. Okay, so we arrive at the Fourier integral formula. Complex form, this is the one we want. And before I write them down, we're ready to do the definition here. So this constant, or what used to be a Fourier coefficient up there, c sub kappa, c sub k, we can also call it the function with a hat of kappa, because this is now a function of kappa, which we're going to call k in a moment. Function of kappa, and it's related to the original function f, so we're going to call it f sub hat, f hat. Okay. So let's go ahead and write these down. They're going to be very nice here. So what we end up is the following. We can express a function as an integral of a Fourier coefficient of k, e to the I kx dx, dk, very important. Integrating from minus infinity to plus infinity, okay? So if you compare this to the sum, it should make a lot of sense. Except instead of calling it C sub k, we're now, because this is going to be very symmetric, we're just going to say it's the Fourier coefficient. It's actually the Fourier Transform. So there's the Fourier Integral, and then the formula for the Fourier Transform is 1 over 2 pi minus infinity to plus infinity f of x e to the minus ikx, and this time dx. Kind of want to avoid making that mistake there, right? We're integrating over k, therefore the argument is x, and down here we're integrating over x, so the argument is the k. So yeah, let's go ahead and write this down. Is the, so f hat of k is the Fourier Transform. I'm going to demonstrate a couple things with this, and you guys can do a problem or two. Transform, that's no. But yeah, when you have these written down together, you can really see the symmetry of it. At this point, it's really satisfying because it's an integral and an integral. There are various conditions on these functions in order that this integral from minus to infinity to plus infinity actually, in order that it converge, right? F of x has to satisfy certain behavior out towards the boundaries, the limits. Okay, good. You know, I'm going to, even as we have the definition here, let me we'll go ahead and erase this. About these limits, we'll get there we'll do that again. It's a really interesting kind of fiddly proof, but this is good enough for what we've done, for what we're doing right now. Okay, here's an important note that goes with this, and I'll just refer back to our driven oscillation. I had given an expression for the energy absorbed by an oscillator that's an undamped oscillator that's being driven. Energy absorbed. So driven oscillations, it was an undamped oscillator. So this is in your notes, but let's write this down again. We have the energy was equal to 1 over 2m, and then this complex expression minus infinity to plus infinity f of t e to the minus I omega t dt complex conjugate squared. Okay. So remember, we had that, and we had seen a couple of things. In certain limits, this just turns into p squared over 2m. But generally, this thing inside here is the Fourier transform of the driving force. Okay. And it's for that frequency omega of our oscillator. That was the driving frequency of the oscillator. And we can compare this expression here to this Fourier transform of the function f of x. Okay. This is, of course, if you express it, function of time, t and omega. So yeah, we've already seen an application of the whole Fourier formalism in this expression right here. Let me consult the clock. Perfect, we've got time. So what I'm going to do next is leave this up here and do an example or two. Maybe leave something for you guys to calculate as well. This was referring back to what we had done earlier. Okay. So what we're going to do is take a very simple function and calculate its Fourier transform. And then we'll set up a more complicated one. But this one actually has all that we need. So let's take a normalized function, f of x equals, and you know what, I'm just going to draw it first. So here's our x-axis, and we want this spike right here. And let's call this minus a over 2 plus a over 2. So it's a wide, the width is a, and the height is going to be 1 over a. I'll just write it down, it's 1 over a. So it's 1 over a when minus a over 2 less than x less than a over 2, and it's 0 when x is greater than a over 2 magnitude. I'll go ahead and do this in the color again. So it's 0 here and a over 2 right here. We don't have to make it normalized, but we have made it normalized, so the integral over this entire thing is 1. So what is the Fourier transform of this function here? It's just a step function, right? F hat of k is 1 over 2 pi integral minus infinity to plus infinity f of x e to the minus I kx dx. Okay, good. We've got the 1 over 2 pi. Now, it's going to be 0 everywhere, minus a over 2, a over 2. So the limits are there, and it is equal to 1 over a, and we have e to the minus I kx dx. So yeah, that's not going to be difficult. So we will have 1 over 2 pi a, and our antiderivative, we have a 1 over minus ik, e to the minus I kx, evaluated, minus a over 2 to a over 2. So once we evaluate this, we'll be done. Okay, so what do we have here? We have 1 over 2 pi a, I've got 1 over k, 1 over negative I, I'm going to leave that there. And then e to the minus I k a over 2 minus e to the I k a over 2. So we're just going to clean this up a bit because there's a sign hidden in here. So let's see, we have, we'll get rid of the minus sign and reverse the order of these. We will have, I'll work with this first here. We'll have e to the I k a over 2 minus e to the minus I k a over 2 over 2I. I got rid of the minus sign and the I and the 2, so I have 1 over pi k a. This is the sine of k a over 2 equals 1 over pi k a sine of k a over 2. I'd actually rather have just the sine of. I would rather have ka. Yeah, let's replace a with 2a, like this. Let a equal 2 times a. That'll just give us a cleaner result here. So then we'll have 1 over 2 pi ka sine of ka. This one will be easier to interpret. We don't need that a over 2 there. But they're both the same. They're both identical. So let's graph this thing and then interpret it. In fact, let's do this. We have draw a new picture, so I'll draw a new picture too. We're going to go minus a to a, and then 1 over 2a, like that. Okay, same dimensions, but I'll just rewrite this. So f of x is equal to 1 over 2a minus a less than x less than a, 0 x greater than a. This works better. So what we've now found, f hat of k is equal to, and we see this graph here, f hat of k is equal to 1 over 2 pi ka. Let's write this. How about like this? 1 over 2 pi sine of ka over k. I'll change the letter again. K times a. Okay. There's what we were finding. This is what we were looking for. And this is what we want to graph before we leave here today. So this is a function of k. So here we had an x-axis. If we want to graph this Fourier transform, we have a k-axis, and we're graphing f hat of k. So ignoring the 1 over 2 pi, it's just a constant. Sine of ka over ka, in the limit as k goes to 0, this limit is 1, okay? So this thing here is 1 over 2 pi. And the first time the sine of k times a crosses the axis is when k times a is equal to pi. Okay. So we would have k is equal to pi divided by a. K is equal to minus pi over a. And then it's going to go like this. It's going to cross the axis here. From then on out, the contribution is very small. It's getting smaller as k increases, and it's half as wide each time. So almost the entire contribution is right here, centered here between this interval. And here's the important point that I want to end with. This is, in a sense, the inverse of this step function, because as a gets smaller, this one gets wider. Okay, so this expression is very important here. Okay, note. So this is a general property. If you take the Fourier transform of something narrow, Fourier transform is wide, and vice versa. Something that's very important in optics, and in a sense, you're already looking at your uncertainty relations, as you'll see when you study quantum mechanics. This is a calculation for that as well. Good, we're going to leave it at that and pick this up again next time. Consult the clock once more. Good, yeah, that's enough for today. So yeah, I forgot about these limits. It's better to go from, like I said, just to get this simpler function, minus a to a. The same point holds. The narrower this function is, it's narrow and tall, and then this thing will be wider and inverse. Good, see you guys next time.